Good morning, our team Forrest. The team members are Ahmed Sulaiman, Omar Touni, Rad Adel, and Sami Hosni, and our supervisor is Dr. Amr Wassal. This is our agenda for today. We'll give an introduction about our project and its features. Then we'll talk about system architecture and the GUI. After that, we'll talk about the challenges that faced us and the timeline that we followed through the year. At last, we'll show a demo of our project and discuss our future work. As walking is the first thing that a human learns, and it is his first step in his journey to discover the world, and as the main task of humanoid robots is to do the tasks that humans can do, then the first thing that a robot needs to learn is walking like humans. From here came our idea, which is to implement a walking algorithm that makes bipedal robots walk like humans. Our main goal was to implement the walking algorithm that makes robot walks on flat planes only. We bought a bipedal robot kit, which is shown here on the figure, and we started working on it. But due to COVID-19, we couldn't continue our work on the hardware, as we were missing some components, and in addition to that, it was very hard on only one person to use the kit and test any walking algorithm we implement. So we got a permission from Dr. Amr and the board of the department to continue our project on a simulation tool. So our goal from this project has changed. So what does our project do now? It can walk on flat plane. It can also follow a path that's given to it by the user. It can walk on inclined planes up to 11.45 degrees. It also has a dynamic balancing system, which allows the robot to adapt to any change in the inclination angle of the floor it is walking on. The simulation tool we used is called Robots. It is an open source robot simulator. It is multi-platform. It provides a complete development environment to the model, program, and simulate robots. The robot model that we used in the simulation tool is called Robotis OP3. It is manufactured by the Korean company Robotis. It contains 20 motors, 6 per leg, 3 per arm, and 2 in the head. It also contains an accelerometer and a gyroscope sensor. As for the system architecture, there are two approaches to make a robot walk. A modern approach, which includes machine learning. Its idea is to teach the robot how to walk using reinforcement learning. The other approach is the one that we implemented, which relies on the dynamics of the robot. We make sure that the center of mass is in the area of the leg that's standing on the floor. We use inverse kinematics to calculate the values of the joint angles that need to be sent to the robot's motors in order to reach a certain position. This is the block diagram of our project. We have the robot module. This module is an interface between our code and the robot model in the simulation. We have the GUI module, where the user can draw a path and watch the robot while walking on this path. We have the inverse kinematics module, which takes the Cartesian position that the robot needs to reach and calculates the motor angles values that's sent to the robot. And we have the controllers module. The controllers module is the core of our project. We'll discuss it in the next couple of slides. The controllers module is divided into many sub-modules. The first two modules are responsible for balancing the robot on inclined planes, one for the pitch angle and one for the roll angle. Both of them creates an instance of the PID controller. Both of them reads the gyroscope and accelerometer sensor readings, and they initialize the PID controllers. The inclination pitch controller outputs the values that needs to be sent to the motors at the ankle of the robot, while the inclination roll controller outputs the values that needs to be sent to the motors at the feet of the robot. And here is a part of the walking of the controllers that's responsible for walking. It contains 3 modules: path controller, walking controller, and pattern generator. The path controller is the one that takes the SVG path from the GUI. It divides this path to many points and vectors, and it calculates the steps that the robot needs to follow in order to walk through this path. It sends it sends the step length, which means the distance that's cut by each step, and the duration of this step to the working controller. The working controller takes this information and send it to the pattern generator. The pattern generator outputs the step pattern that the robot needs to do in order to make this step. The step pattern is the values that the robot reach during taking the step, which means the Cartesian which means a series of Cartesian points that the robot reaches while walking. It takes this information and sends it to the IK module, which is the inverse kinematics module, to calculate the values needed to be sent to the motors, and the bus controller keeps track of the current position of the robot. So it sends this current position to the GUI module in order to make the user watches the robot while walking on its path. So the modules we have in our project is the robot physical module, which is we used the robotics OPS new module as our goal was not to implement the robot model itself. About the GUI module, we used Electron framework to make the GUI more interactive and user friendly. As for the robot interface, the inverse kinematics, the working pattern generator, the balancing and PID controllers, and the bus controller, which are the core of the project, they are all implemented from scratch without using any frameworks. The GUI is a Windows application. It's implemented by using Electron and React frameworks. It allows the user to draw an SVG path. It also contains a window which makes the user watch stream from the Webbots simulation tool to allow the user to watch the robot while walking. It also allows the user to stop and play the simulation and to reset the simulation and start a new one. This is the tools we used. The simulation tool was Webbots, our IDE was Visual Studio Code, our version control is GitHub, and Electron for implementing the GUI. The challenges that we faced was 4 challenges. The first one is the unobvious documentation of Webbots. Webbots really have very bad documentation. Nothing was clear in this documentation. Everything that we needed to do in the simulation, we had to try and figure it out ourselves. So we didn't refer to the documentation in almost all the cases. Second challenge is the lack of resources, as walking differs from one model to another. So it was very hard to find some resources that help us to make our model work. Another challenge was handling 2 threads using WebSockets. This challenge appeared while implementing the GUI and connecting it to our project. We need to have 2 threads, one for the control of the project, which is the main loop of the project, that reads the sensors, we calculate the pattern, we generate a pattern and calculate the values, and the other thread was responsible for getting any actions that the user do from the GUI. So we needed to handle these 2 threads together. The last challenge and the biggest challenge that faced us is the COVID-19, which changed the whole idea of our project. This is the timeline that we followed through the year. During July and August was the idea generation. Then from September, October and November there was the research. We ordered the robot kit and assembled it. December and January were the projects and finals. February and March we implemented the drivers needed for the hardware, which are the communication protocol, the motor control drivers, and the ADC for reading the sensors. We also implemented a version of the motion pattern that works on our hardware model. We tested it and we had good results. But after that, the COVID-19 problem started. We tried for about a month to continue working on the hardware, but it was really very hard. So after getting the permission to work on simulation tool, we started implementing that working algorithm on the simulation tool. Then we implemented the walking pattern of the robot on inclined floors, and we implemented the path module. After that, during that we were testing our project, and we started our documentation in June. So let's now watch a demo of our project. This is the connect window. We click connect to the WebSockets. In the upper left window, there is a live stream from the WebBot simulation tool. It is the environment that is loaded, and this is our robot model loaded here. On the upper right part, this is where the user can draw a path. So here he draws a path. The path can be curved. Then click start. Here is a path. Here is the path recognized by the robot. It is similar to the original path, but the robot adds some checkpoints at the corners of the path in order to make sure that the robot is following its path. Then we click start. You can see here the robot starts walking. It rotates around itself, so it can follow the angle of the path. As you see here, the green arrow indicates the current position of the robot, and the green line indicates the distance cut by the robot on this path. Here, when it reaches this checkpoint, it rotates around itself in order to continue walking on the new vector or the new direction in the path. As you see here, it almost reaches that curve. So here the robot starts walking and rotating around itself at the same time, takes some steps, then rotates, some steps and rotates, some steps and rotates, and it continues walking until it reaches the final position. So here it stops. It can also walk inclined floor. This floor has an inclination angle of 11.45 degrees. It can adapt and walk on it. And here it can walk on flat and inclined floors together. Here it starts on flat, then it finds itself on an inclined plane upwards. It adapts to this change in the inclination. Then it finds itself on a flat floor, then on inclined floor again, but this time is downwards, and then it reaches a flat plane. It can adapt to these changes in the inclination and continue its walking. This is our future work. First of all, we already bought the hardware kit, so we will implement this algorithms that we implemented on the simulation tool. We implemented on the hardware robot. We also want to implement a recovery system that allows the robot to recover. That allows the robot, if it falls on the ground for any reason, it can stand up again and continue walking. We want the robot also to handle external forces, so it can lift anything, and we want to participate in the humanoid soccer competition. Thank you.